In the last video, you learned about Elixir processes, and I showed you one way of creating a process by using the spawn function and passing it an anonymous function to run in the new process. By the way, there's another spawn function with an arity of 3. Take a guess at when you'd use this spawn function. Well, if you're not sure when this would get used, let me help you by naming these 3 parameters. Okay, with these parameter names, it should be pretty apparent when this spawn function is used. It's used when you want to run a named function in a new process. To use this alternate spawn function, you just pass in the module name, then you pass in the function name as an atom, and lastly you pass in a list with the arguments that should be used in this function. So let's think about the processes we created in the last video with this code right here. Do you think the process that was started with this code is a long-lived or short-lived process? Okay, you might be wondering, what do I mean by long and short-lived? Well, by short-lived, I mean the process runs for a finite period of time, just long enough to accomplish its task, and then it stops. And by long-lived, I mean the process runs, doing work, or possibly waiting to do some work, for an indefinite period of time. Well, using those basic definitions, you'd probably conclude that the process we created here must have been a short-lived process. I mean, the function we ran in the new process only logged something out and sent a message, and then there was nothing else to do, so it must have been short-lived, right? There's actually a way to check if a process is running, which is done by calling a function in the process module named alive and passing in a... Actually, what do you think I should pass in here? Well, the same thing we used to send messages, the process identifier, which is an address, if you will, for each process created in the beam. Let's check to see if the process spawned on line 11 with this PID is still running. Now, this PID isn't bound to a variable, and we need it to pass it into the alive function. So are we stuck, since we didn't bind a variable to this PID return value? Nope. There's a couple of ways of accessing this PID right here. There's a helper function named PID, which we can use in IEX like this. I'll call PID, passing in the 3 integers you see here. Another way of accessing the PID returned on line 11 is to call the vHelper function, passing in the line number to retrieve the value returned on that line. So I'll fetch the PID returned on line 11 by calling the v function and passing in the line number 11. And as you can see from the response, the process spawned on line 11 isn't alive, it's dead. So what are these short-lived processes good for? Well, they're really good at performing work on what I'll characterize as relatively slow tasks. For example, things like serving a web page, or servicing an API request, or making an API call. Do you see what's common among these examples? They all include I/O, which is inherently slow. Here's a way of thinking about processes that I think can be helpful to a new Elixir programmer. You can think of a process as sort of a container for doing work, whatever that work might be. And if you want to do lots of concurrent work, well, you just need to put the work in a process or lots of processes, and then the Beam's scheduler will distribute this work that each process needs to perform across all the CPUs in your computer. Let's consider an example of how short-lived processes can be beneficial. Here's a list of 10 IP addresses for 10 voting machines. Now imagine we need to communicate with these voting machines to download their vote totals every few minutes, and then we need to sum the vote count from all 10 machines. So how should we do this? Well, first of all, there isn't really 10 voting machines to talk to, so I'm just going to simulate this step with the following anonymous function. The anonymous function will take an IP address as its parameter, then I'll create a variable named votes, and I'll bind it to a random number by calling the enum module's random function, and I'll pass in a range of numbers to pick from. I'll say the random number should be between 225 and 275. Next, I want to simulate a delay which would be normal for an API call. So how can we simulate a delay? Well, I've got bad news and good news. The bad news is there isn't a way in Elixir to pause a process, but the good news is that there is a way to pause a process in Erlang. And of course, as you learned a long time ago, calling an Erlang function from Elixir is easy, direct, and rather painless. Do you remember how to make an Erlang function call from Elixir? It's been a while since I showed you, but basically you use a colon followed by an Erlang module name, which in our case will be timer. Then you can call a function using dot notation. So I'll call the sleep function, and I'll tell the process to sleep for whatever random number is bound to the votes variable, so it'll sleep for somewhere between 225 and 275 milliseconds. Lastly, I'll just return the votes. Now, one way of polling all 10 of these machines would be to do something like taking the voting machine IP address and piping it to map, and then passing in our simulated API call function. Then we can pipe the result of map to the sum function, and then, just to see the summed value, I'll pipe the result to inspect. Let's see if this works. I'll run the Elixir command, providing the file to run, and after about 2 to 3 seconds, we get a result. Okay, so that worked, but can we make this overall process faster? Yep, we sure can. The current implementation runs all 10 requests in sequential order. But we could run these 10 requests concurrently and cut our time down by a factor of about 10. So how do we achieve this? Well, we just need to create a process for each of the 10 API calls. That way all 10 requests happen concurrently rather than in series. Let me provide a visual for how we're going to do this. Okay, first of all, we've got this list of IP addresses that exists in a process I'll call the master process, for lack of a better name. We're going to call enum_map on the list, which will send each IP address to a function, and this function will generate a new process and return the new process's PID. Now, the new processes will make simulated API calls to the provided IP address. Then the result of making the API call will get sent back to the master process via message passing, and it'll sit in the master process's mailbox for a moment. Now, again, the result of calling map here will result in a transformation of IP addresses to PIDs. So what do we do with these PIDs? Are these PIDs even useful to us? Well, they can be, especially if you think about the 10 messages in the master process's mailbox. Do you think these 10 messages in the master process's mailbox are in a particular order? In other words, do you think the first message is the API response for the first IP address, and the second message is an API response for the second IP address, and so on? Well, the answer to that is nope. Absolutely not. Messages are placed in the mailbox as soon as they're available. So if the 10th process completes before the first process, then its return value will be first in the mailbox. Okay, so how can we properly map the values in the mailbox into the proper position in a list? Well, the list that's returned from map has 10 unique PIDs. So what if the messages we sent from each of the 10 child processes back to the master process included the sending process's PID in addition to the return value from the API call? Then we could simply match the PID in the list to the corresponding PID in the process mailbox. And we could then place the vote counts in a list position that corresponds with the machine's IP address position. All right, I'm going to make a module to handle creating the worker processes, and I'll call the module the worker module. This module will have a start function that will be responsible for spawning new processes to do the API calls. We'll have the start function receive an anonymous function as its parameter, which will be the function that does the actual work we want completed. To create a process, I'll call spawn, then I'll pass in an anonymous function, and then inside this function, I'll call the send function to send a message. But what process ID should we send the message to? Well, it's going to be the process that calls the start function. So we could have it get passed in as a parameter, or we could simply create a variable named PID and bind it to the result of calling the self function. Now back in our send function, I can just pass in the PID we defined up here. Okay, the next parameter to the send function is the value we're wanting to send. So what data payload should we send? Well, as I described in this visual, we should send a message that includes the sending process's PID as well as the retrieved votes. To do this, I'll send a two-element tuple where the first element is the spawned process's PID, which I can get by calling the self function, and the second element will be the result of calling the passed function. Okay, that's all we need to do for the start function. Now let's go use the start function we just made. So I'll first get rid of the direct usage of the simulated API call function, and instead I'll pass in an anonymous function that's provided the IP address. Then I'll call our new worker module's start function. The start function expects a function as its parameter, so I'll pass in another anonymous function, which will make the simulated API call, and we'll pass in the IP address. Let me reiterate what's happening with this line of code here. This outer function here will get called for every IP address. Then the start function is called, which will spawn a new process and return the new process's PID. The new process will get past this inner function, and I will call this function to do the work of fetching the votes. So the result of this line is that the list of IP addresses are transformed into a list of PIDs, and 10 separate processes are spawned that make 10 concurrent API calls. I'm going to go ahead and pipe the result of this line into IOInspect just so you can see the list of PIDs that come out of this call to map. For the moment, I'm going to comment out the call to sum and inspect. We'll uncomment these lines in just a few moments. Okay, so after a short period of time, all 10 processes that were spawned should send 10 messages back to the master process. So let's do this. I'm going to call sleep again, and I'll pass in 300 milliseconds, which is just enough time for all 10 simulated API calls to complete. Then I'm going to call process info for this process, and I only want to see this process's mailbox, so I'll pass in the message as Atom, and then I'll pipe what's returned from this info function to inspect. Now I'll run our script again, and we see a list of 10 PIDs from this call to IOInspect, and then we see the contents of the master process's mailbox, which has 10 messages that are these two-element tuples you see here. Each one of these messages corresponds to one of these PIDs in this list, but notice the messages are out of order because each API call took a varying amount of time. So all we need to do now is figure out how to map these PIDs in this list to their corresponding messages in the mailbox. To do this, I'll write another function in the worker module named wait, which will receive a PID as its parameter. Then in the body, I'll use the receive macro to pattern match on a two-element tuple where the first element matches the passed PID, and the value in the second element is bound to the result variable. Then I'll use a right arrow and just return the result. Actually, does this look right to you? There's a problem here that we've seen before. The way I'm using the PID right here isn't actually asserting that the first element must be the value passed into wait. It's just rebinding the value of the first element to the PID variable. This isn't actually what we want. We actually want to match on the value of the PID that's passed into this function. So how do we fix this? Well, to actually assert that the first value should be the value bound to the passed PID parameter, I need to use the pin operator, which is something we covered many videos back. So there's something subtle but noteworthy happening in the receive macro. We're going to use this wait function in a moment here, and when this function gets called, this receive macro will run and it'll check the first message in the mailbox to see if it matches this pattern here. If the first message doesn't match this pattern, the next message is checked to see if it matches this pattern, and each subsequent message is checked to see if any of the messages match this pattern. If no messages in the mailbox match this pattern, then the receive macro, as written here, will block waiting for a message that matches this pattern. This message pattern matching and potential blocking could be totally fine, or it could be problematic depending on the situation. Keep this behavior in mind as we learn more about processes. Okay, back to our example. Let's use our new wait function down here. I'll pipe the list of PIDs to enum map, and I'll pass in the worker module's wait function, well, at least a captured version of it. Next, I'll uncomment sum and inspect, and we'll try running this script again, and it worked. We were able to make 10 API calls concurrently, which was much faster than the 2 to 3 seconds it took before. In fact, it took less than 300 milliseconds, and then we collected all the results and summed them together, and notice there are no messages in the master process's mailbox because we pulled them all out and handled them. Well, let me ask you this. What if one of these 10 processes we spawned failed for some reason? What do you think would happen? For example, imagine that the very first spawned process died almost immediately because the voting machine was turned off, or maybe because there was some other network issue. Would it make sense to let the other 10 processes keep working? Well, maybe and maybe not, depending on the situation. In our example, the goal was to get the voting results of all 10 machines and sum the results together, and if one of the machines isn't available, it would be a waste of resources to make the other 9 API calls when there's no chance of getting to the desired result. So what should we do in this type of situation? Well, that's what we'll talk about in the next video.